What if everything you can possibly see, every star in our night sky, and every galaxy captured by our most powerful telescopes represents only a fraction of reality? What if the cosmos we call home is just a single bubble floating in an endless sea of other, entirely different universes? Gazing up at the stars often fills us with a sense of awe, a feeling of confronting something vast and ancient. Yet, that breathtaking view might be profoundly limited. The observable universe stretches for billions of light years in every direction, a realm of unimaginable scale that contains hundreds of billions of galaxies. But this incredible expanse has a boundary, a limit to how far we can see, governed by the finite speed of light and the age of the cosmos itself. This raises a question so fundamental, so deeply unsettling, that it has captivated thinkers for centuries. What lies beyond that boundary? Is there simply nothing? Or is there something far stranger, something that challenges our very understanding of existence? For generations, this question belonged to the realm of philosophy and pure speculation. Today, however, it sits at the very frontier of theoretical physics and cosmology. Scientists are now constructing serious, mathematically rigorous models that propose answers more incredible than most science fiction. These are not just wild guesses. They are theories born from the deepest puzzles within our current understanding of the universe, from the strange nature of quantum mechanics to the mysteries of the Big Bang. The quest to understand what lies beyond our universe is driven by a fundamental human trait, an insatiable curiosity that refuses to accept that there is a final wall, an ultimate outside that we are forbidden from exploring even with our mind. It is a journey that pushes the limits of imagination and reason, forcing us to reconsider everything we think we know about space, time, and reality itself. In this video, we are embarking on that very journey. We will explore 25 of the most compelling, mind-bending theories about what might exist beyond our cosmic horizon. We will venture into the possibilities of a multiverse where countless other universes bubble into existence, each with its own unique set of physical laws. We will grapple with the idea of higher dimensions, realms so alien that our three-dimensional minds can scarcely picture them. We will even consider theories that suggest our entire universe could be a projection, a simulation, or something even more bizarre. This is not a tour with easy answers, but an exploration of the deepest frontiers of human thought, where the line between established science and profound speculation becomes beautifully blurred. So, prepare to have your concept of reality stretched to its absolute limits, as we begin our countdown of 25 theories about what lies beyond our universe. And so we arrive at our first and perhaps most famous theory, the concept of the multiverse. This idea proposes that our universe is not the entire story, but merely a single chapter in an infinitely vast library of realities. Each of these other universes could be a self-contained cosmos, born with its own unique set of physical laws and constants. In one universe, gravity might be so strong that stars form and burn out in just a few million years. In another, the fundamental forces might be so weak that matter never clumps together to form galaxies at all. Our universe, with its specific, seemingly fine-tuned parameters that allow for stars, planets, and life, would then be just one fortunate roll of the cosmic dice. Where does this astonishing idea come from? It doesn't spring from pure fantasy, but from the mathematical edges of our most successful theories, particularly the study of the Big Bang known as cosmic inflation. One leading version, called eternal inflation, paints a picture of a meta-reality, a grand, eternally expanding background. Within this seething, energetic fabric, random quantum fluctuations can spark localized events, causing pockets of this background to stop inflating and instead settle down into stable, bubble-like universes. Our entire observable cosmos could be the interior of just one such bubble, floating in an endless, frothing sea where new bubbles are continuously being born. We can't see these other bubbles because their light can never reach us, as the space between us is expanding faster than the speed of light. This leads to a truly staggering implication. If this process is truly eternal and infinite, then every possible permutation of physical laws must exist somewhere. There could be a universe where you made a different choice this morning, a universe where dinosaurs never went extinct, and universes so alien that we lack the language to even describe them. While this sounds like the plot of a science fiction novel, it's a serious, albeit highly speculative, attempt by physicists to answer why our universe seems so peculiarly hospitable to life. In an infinite multiverse, it's no longer a miracle that we find ourselves in a universe that allows our existence. It becomes a statistical certainty. Of course, this theory is not without its critics who point out its current untestable nature. Yet it stands as a monumental idea, the first step in our journey beyond the familiar, forcing us to contemplate a reality of literally cosmic proportions. While the multiverse suggests an endless expanse of parallel realities, another profound theory offers a different vision of eternity, not through space but through time. This is the cyclic model, a concept that paints the cosmos not with a single, definitive beginning, but as a participant in an endless, rhythmic dance of birth, death, and rebirth. Imagine the universe not as a one-time event, but as a phoenix, perpetually rising from its own ashes in a cycle that has no true start and no final end. What lies beyond our current expanding universe, according to this view, is not an empty void or a collection of other bubbles, but the next chapter in an infinite story where our universe is both the conclusion and the prologue. This elegant idea directly challenges the standard narrative of a singular Big Bang emerging from a singularity. Instead, it proposes that our universe's current period of expansion will eventually slow, halt, and reverse. Under the immense pull of gravity, all matter and energy would be drawn back together in a cataclysmic event cosmologists call the Big Crunch. This wouldn't be a simple rewinding of the film. It's a dramatic collapse where galaxies, stars, and even the fabric of spacetime itself are compressed into an incredibly hot, dense state. But here's where the cycle renews itself. This ultra-dense state might not be a final death. Instead, it could act as a cosmic seed, triggering a new Big Bang and launching a fresh universe into existence, one potentially with slightly different properties than our own. Some of the most compelling support for this cyclical nature comes from the complex world of string theory. Certain versions of this framework suggest that the collision of mysterious, multidimensional objects called branes could be the engine that drives these cosmic cycles. In this ekpyrotic scenario, our three-dimensional universe exists on one such brane. A cyclical dance with a parallel brane in a higher dimensional space could periodically bring them together, with each collision releasing enormous energy that we would experience as a Big Bang, setting off a new period of expansion. After the branes move apart and the universe evolves, gravity would eventually pull them back for another collision, starting the process all over again. The implications of a cyclic universe are staggering. It removes the need for a definitive moment of creation, replacing it with an eternal, self-sustaining process. There was never a before the Big Bang in the traditional sense. There was simply the previous cycle. Our universe, with all its history from the first stars to the rise of life on Earth, would be just one iteration in an infinite series. This also offers a potential solution to the mystery of why our universe began in such a highly ordered, low-entropy state. It could have been reset or smoothed out during the transition from the Big Crunch to the subsequent Big Bang. While evidence for the cyclic model remains elusive, it provides a profoundly different and strangely comforting perspective on our place in the cosmos, suggesting that existence itself is an eternal, repeating rhythm echoing through time. But if the cyclic model redefines the nature of time, our next theory challenges the very nature of space and dimensionality. Imagine for a moment that every person, every planet, every galaxy you have ever seen is not truly three-dimensional. What if the rich depth of our reality, the very sense of volume and substance, is an elaborate illusion? This is the breathtaking proposition of the holographic principle, an idea so radical that it suggests our universe is a cosmic projection, a hologram of staggering complexity. According to this theory, what truly exists beyond our observable universe at its farthest boundary is not more space, but a two-dimensional surface containing all the information needed to generate the three-dimensional world we experience. This concept emerges from a surprising place, the study of black holes. Physicists discovered that the amount of information or entropy a black hole can contain is not proportional to its volume, as you might expect, but to the surface area of its event horizon. It was as if all the information about everything that fell into a three-dimensional black hole was somehow encoded on its two-dimensional boundary. This led to a revolutionary thought. If this is true for a black hole, could it be true for the entire universe? Our cosmos has a horizon too, the limit of what we can see. The holographic principle daringly proposes that our entire universe is a vast hologram, with all the information that defines every particle, every force, and every event in our 3D world actually stored on a distant, two-dimensional surface at the cosmic edge. A powerful analogy is to think of a credit card hologram. That small, flat sticker can create a stunningly realistic 3D image when light hits it. In a similar way, the holographic principle suggests that the two-dimensional boundary of our universe acts like that sticker, and the three-dimensional universe we inhabit is the projected image. The pixels of this cosmic projector are unimaginably tiny at the Planck scale, but the principle is the same. Every event that happens here, from a supernova explosion to the firing of a neuron in your brain, corresponds to a specific change or interaction on that remote, flat surface. The depth, the texture, the very solidity of our world would be a phenomenal illusion generated from a reality with one less dimension. The implications are staggering. It would mean that the universe is fundamentally simpler and more constrained than it appears. It also provides a potential framework for unifying the two great pillars of modern physics: Einstein's general relativity, which describes the large-scale structure of space-time, and quantum mechanics, which governs the tiny subatomic world. By describing the universe as information on a surface, the holographic principle might offer a way to see gravity not as a fundamental force, but as an emergent property, a consequence of the quantum interactions on that lower dimensional boundary. While this remains a highly theoretical framework, it completely inverts our intuition about reality, suggesting that the ultimate truth of the cosmos is not found in the space around us, but encoded on a distant, fundamental screen at the very edge of existence. Building on the idea that our reality might be a projection, what if the universe we perceive is not merely an illusion, but is actually missing entire dimensions? To grasp our next theory, we must venture beyond the familiar three dimensions of space and one of time. We have to contemplate the possibility that our cosmic home is like a single page in an impossibly vast, multidimensional book. This is the realm of brane cosmology, a concept that springs from the complex mathematics of string theory and offers a stunningly visual answer to what lies beyond. String theory itself is an attempt to solve one of the biggest puzzles in physics, unifying Einstein's general relativity, which governs the very large, with quantum mechanics, which rules the very small. It proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating strings. And for the math of these vibrations to work, the theory requires more than the 4 dimensions we experience. It needs 10 or even 11 dimensions of space-time. Brane cosmology takes this abstract idea and gives it a powerful physical form. It suggests that our entire universe is a 3-dimensional membrane, or brane for short, floating within a higher dimensional arena known as the bulk. Think of it this way. Imagine our universe is a single, impossibly thin slice of bread hovering in a grand cosmic loaf. This slice is our brain. Everything we know, every galaxy, every person, every atom is stuck to this slice. The forces that govern our world, like electromagnetism and the nuclear forces, are like a special glue. Their effects are confined to the surface of our brain and cannot easily escape into the higher dimensions of the bulk. But gravity, according to this model, is different. It is so fundamental to the fabric of spacetime that it can leak out of our brain and seep into the bulk. This could explain why gravity is so phenomenally weaker than the other fundamental forces. Its strength is diluted as it spreads out into these extra dimensions. This leads to an electrifying possibility. If our universe is one three-dimensional brain, then there could be countless other brains floating in the bulk, each one a complete parallel universe. Some might be very close to ours in the higher dimensional space, perhaps just a microscopic distance away in a dimension we cannot perceive. These parallel brains could have entirely different physical laws and constants. Life as we know it might be impossible on them, or it might have evolved in forms we can't even imagine. We are, in a sense, neighbors with other entire cosmoses, yet separated by a fundamental dimensional barrier that makes direct contact or observation seemingly impossible. The most dramatic implication of brane cosmology provides a compelling alternative to the standard Big Bang theory. What if our universe's violent birth was not a singularity emerging from nothing, but the result of a cataclysmic collision? This is the ekpyrotic model, which suggests that our Big Bang was ignited when our brain smashed into another parallel brain moving through the bulk. The immense kinetic energy of that collision would have been converted into the seething hot plasma of particles and radiation that filled the early universe, setting off the expansion we observe today. After the collision, the brains would have moved apart, and the cyclic nature of the bulk could mean they are on a course to collide again in the far, far future, potentially creating a new universe in an endless cycle. So, what lies beyond our universe, according to this view, is not empty space but a higher dimensional ocean, a bulk, teeming with other cosmic membranes, any one of which could contain a reality as rich and complex as our own. Now, we move from the physical to the digital, from membranes and holograms to a theory that reimagines the cosmos not as a natural phenomenon, but as an artificial creation. This is the simulation hypothesis, an idea that has leapt from the pages of philosophy and science fiction into serious debate among technologists and physicists. It proposes a startling answer to what lies beyond our universe, a layer of reality far more fundamental than our own, where our entire cosmos, from the largest galaxy to the smallest quark, is nothing more than a sophisticated simulation running on a computer of unimaginable power. In this view, the laws of physics are not fundamental truths, but simply the rules of the program, the underlying code that governs the virtual reality we mistake for existence. The logic behind this hypothesis is deceptively simple and rests on a few key assumptions. First, if a civilization ever becomes technologically advanced enough to create realistic, immersive simulations of its own history or of entirely fictional worlds, it is reasonable to assume it would create many of them, perhaps even billions. Second, within those simulations, advanced artificial intelligences or simulated beings could eventually become conscious, believing their digital world to be real. Now, if this is possible, then a simple statistical argument follows. There would be one original, base reality and a potentially vast number of simulated realities. Therefore, the odds that we are living in the one and only original reality are astronomically small. It is far more probable that we are minds in one of the countless simulations. This isn't an entirely new concept. It's a high-tech version of age-old philosophical puzzles. The ancient Greek philosopher Plato pondered if what we perceive are just shadows on a cave wall, mere reflections of a truer reality. The simulation hypothesis updates this allegory for the digital age, suggesting the cave is a server farm and the fire is the processing power of a super-intelligence. Proponents like Oxford philosopher Nick Bostrom have formalized this reasoning, arguing that at least one of three propositions must be true. 1. Virtually all civilizations like ours go extinct before reaching a post-human stage capable of running such simulations. 2. Even if they reach that stage, almost none have any interest in running simulations of their ancestors. Or 3. We are almost certainly living in a simulation right now. What would the evidence for such a simulation look like? Some scientists speculate that if our universe is a construct, there might be telltale signs in the fabric of reality itself, tiny artifacts or shortcuts a programmer might have taken. These could manifest as subtle glitches in the laws of physics, perhaps observable in the behavior of high-energy cosmic rays. Others point to the seemingly digital nature of quantum mechanics, where particles exist in blurred states of probability until observed, almost like a computer rendering details only when a player looks at them to save processing power. The finite speed of light could be seen as a limit on how much data can be processed and displayed at any given time, a cosmic frame rate. The implications of this theory are profound, touching on everything from free will to the meaning of life. If this is a simulation, then the programmers are, for all intents and purposes, gods. They could pause, rewind, or alter the code. They might intervene directly, events we could misinterpret as miracles or supernatural phenomena. The purpose of our existence could be as mundane as a historical research project, a form of entertainment, or even a cosmic art installation. While many physicists dismiss the idea as untestable and therefore unscientific, it forces a crucial confrontation with the nature of consciousness itself. If a simulated mind can be truly conscious, then the substrate of that consciousness, whether biological neurons or lines of code, may not matter. The experience of being is what feels real, regardless of its origin, leaving us to wonder if there is any practical difference between a perfectly simulated reality and a base reality at all. But if the simulation hypothesis makes our reality feel like a complex software program, our next theory takes this idea of a structured cosmos to its ultimate, most austere conclusion. It proposes that the universe is not merely described by mathematics, but that it literally is mathematics. This is the mathematical universe hypothesis, championed by cosmologist Max Tegmark, and it presents a vision of existence so pure and abstract that it challenges the very distinction between the physicist and the mathematician. According to this radical perspective, what lies beyond our specific universe is not more space or other physical realms, but the vast, unchangeable, and eternal landscape of all possible mathematical structures. To grasp this, we need to reconsider a very basic assumption. We tend to think of the universe as a physical entity that we can describe using the language of mathematics. The laws of physics in this traditional view are like a user manual for a complex machine. They help us understand how the machine works, but the manual is not the machine itself. The mathematical universe hypothesis flips this relationship entirely. It suggests there is no machine separate from the manual. The mathematical description is the reality. Every particle, every force field, every ripple in spacetime is not just obeying mathematical rules, it is a manifestation of a mathematical pattern. Our cosmos, in its entirety, is one specific, self-consistent mathematical structure. Think of it like a triangle. In the abstract world of geometry, a triangle defined by certain angles and side lengths has immutable properties. It exists as a perfect idea, regardless of whether anyone ever draws one in the sand. Tegmark's hypothesis asserts that our universe is akin to that abstract triangle, but vastly more complex. It is a specific mathematical object, and we, the stars, the planets, conscious beings, are simply patterns within that structure. Our perception of a physical, tangible world is just how this particular mathematical pattern appears from the inside. The laws of physics are then simply the inherent properties of this specific mathematical object, much like the angles of a triangle always adding up to 180 degrees are its inherent properties. This leads to the breathtaking implication about what lies beyond. If our universe is one mathematical structure, then every other self-consistent mathematical structure also exists in a very real sense. There is a universe corresponding to the simple equations of Euclidean geometry. There is a universe for every possible configuration of Stephen Hawking's no-boundary proposal. There could be a universe governed by the rules of a Sudoku puzzle, or one that perfectly embodies the complex symmetries of a Lie group. These other mathematical realities are not located in some faraway space. They simply are in a Platonic realm of perfect forms. Our universe is just one entry in an infinite, mind-bogglingly diverse catalogue of mathematical possibilities. This idea offers a dramatic answer to the ancient question of why mathematics is so unreasonably effective at describing the natural world. If the universe is inherently mathematical, its effectiveness is no longer a mystery, it's a tautology. It also provides a potential resolution to the puzzle of why our universe has its particular set of physical constants. In an infinite landscape of all mathematical structures, ours is simply one that, by its specific properties, allows for the complexity necessary to harbor conscious observers who can ponder their own existence. This is a form of the anthropic principle applied to the entire domain of mathematics. We don't find ourselves in a universe with life-friendly laws because of luck or design, but because we could not find ourselves anywhere else. Of course, this hypothesis is not without its profound challenges. The most pressing question is, what gives these mathematical structures their reality? If a universe is defined by a set of equations, does it exist even if there is no physical substance to it, no one to observe it? Tegmark would argue yes, that mathematical existence and physical existence are one and the same. Furthermore, the hypothesis pushes the boundaries of what we mean by existence itself, venturing into deep philosophical territory. Yet, it stands as a monument to the power of abstract thought, suggesting that the ultimate nature of reality might be found not in a particle accelerator, but in the timeless, placeless truths of mathematics. But what if the order we perceive in our universe is not the rule, but a fleeting, improbable exception? This brings us to one of the most bizarre and unsettling theories on our list, a concept that emerges not from contemplating other worlds, but from the fundamental laws of disorder right here in our own. This is the Boltzmann brain paradox, a thought experiment that turns the nature of consciousness and reality into a terrifying cosmic lottery. It suggests that what lies beyond our familiar, structured cosmos might be an eternity of pure chaos, a void where self-aware minds can suddenly flicker into existence from nothing more than a random quantum fluctuation, only to vanish just as quickly. To understand this strange idea, we need to revisit one of the most fundamental principles in physics, the second law of thermodynamics. This law states that the universe as a whole is constantly moving from a state of order to a state of disorder, a measure known as entropy. Think of a hot cup of coffee left on a table. It will inevitably cool down, its heat spreading out into the room until everything is the same temperature. It will never spontaneously heat up again on its own. The entire universe is following this same path, slowly but surely evolving toward a state of maximum disorder, a featureless soup where no energy can flow, often called the heat death. In this final state, nothing happens. It is the ultimate silence, but here's where the paradox enters. In the 19th century, physicist Ludwig Boltzmann made a crucial observation. Even in a universe that has reached maximum entropy, random fluctuations can occur. Given enough time, an infinite amount of time, the atoms and energy in this chaotic soup will, by pure chance, occasionally arrange themselves into incredibly ordered states. It is statistically possible, though astronomically unlikely, for all the air molecules in a room to suddenly rush into one corner. It is even more unlikely, but still possible, for a fully formed, living brain to spontaneously assemble itself out of the chaos, complete with false memories of a past life in an ordered universe. This hypothetical entity is what scientists call a Boltzmann brain. The paradox becomes truly disturbing when we apply it to our own existence. We believe we are the products of billions of years of cosmic evolution, living in a universe that began in a highly ordered, low-entropy state, the Big Bang. But if the universe is truly eternal and infinite, then the random, spontaneous fluctuation of a single, self-aware brain is vastly more probable than the gradual, structured evolution of an entire universe filled with stars, planets, and billions of conscious beings. The odds of a lone brain popping into existence with a perfect memory of reading this sentence are infinitely higher than the odds of this entire video, you, and the complex cosmic history behind you all being real. Therefore, if our universe is eternal, the statistical argument suggests that you are far more likely to be a momentary Boltzmann brain, a flicker of false consciousness in an endless sea of disorder, than a real person in a real, ordered cosmos. This presents a profound philosophical problem for cosmology. The theory of eternal inflation, which gives us a multiverse of bubble universes, also predicts an eternal, high-entropy background. In such a reality, Boltzmann brains would eventually outnumber ordinary observers like us by an infinite factor. So, if our best theories point toward an eternal universe, they also point toward the conclusion that our own experiences are almost certainly an illusion. Most physicists see this not as a likely description of reality, but as a glaring flaw in our current models. The fact that we observe a coherent, low-entropy universe is powerful evidence against the idea of an eternal, inflationary multiverse in its simplest form. The Boltzmann brain paradox thus acts as a crucial sanity check, forcing scientists to refine their theories to avoid this unsettling implication, steering them toward models that naturally explain why our universe began in a special, low-entropy state, making our ordered existence not a statistical fluke, but a fundamental feature of cosmic history. This idea of a cosmic cycle brings us to a particularly elegant and detailed version of the concept, a theory that offers a specific mechanism for how such a rebirth could occur. We've already touched upon the brane-world scenario, but the holographic-universe theory takes this framework and applies it directly to the question of our ultimate origins, painting a picture that is both violent and strangely beautiful. The name itself comes from the Greek word for conflagration or fire, and it perfectly captures the theory's core premise that our universe began not with a bang from a singularity, but from a fiery collision between two parallel worlds. To visualize this, let's return to the idea of our universe as a three-dimensional membrane or brane existing within a higher dimensional space called the bulk. Now imagine another brane, a parallel cosmic sheet, floating on a parallel course in this bulk. According to the ekpyrotic model, these two branes are not static. They are drawn toward each other by a force, perhaps a form of attraction operating across the higher dimensions. They approach each other slowly over an almost unimaginable timescale. What lies beyond our expanding universe in this view is this vast, timeless bulk, and within it, another brane on a long, slow journey toward a destined encounter with our own. The moment of collision is where everything begins. As the two branes smash into each other, the immense kinetic energy of this impact is not lost. Instead, it is converted directly into the raw material of a new cosmos. This energy floods our brain, instantaneously heating it to an incredible temperature and filling it with a dense, homogeneous sea of particles and radiation. This event, from our perspective trapped within the three dimensions of our brain, would look exactly like the hot, dense state we identify as the Big Bang. The expansion of the universe that we observe today is essentially the recoil from this colossal collision, as the two branes bounce off each other and begin to move apart. This model offers elegant solutions to several puzzles that have long troubled cosmologists. One of the biggest is the horizon problem. Observations show that the cosmic microwave background radiation, the afterglow of the Big Bang, is almost perfectly uniform in temperature across the entire sky. But in the standard Big Bang model, there hasn't been enough time since the beginning for these distant regions to have ever been in contact with each other to equalize their temperature. How did they become so uniform? The ekpyrotic model provides a natural answer. Before the collision, the two branes were very close and parallel to each other for a long time. This prolonged period of proximity allowed energy and information to be exchanged and smoothed out across the entire surface of our brane, creating the uniformity we see today before the Big Bang event even occurred. The collision then simply ignited this preconditioned, homogeneous landscape. Furthermore, the ekpyrotic scenario provides a compelling alternative to the concept of cosmic inflation, the brief period of hyper-expansion proposed in the standard model to explain the universe's smoothness and flatness. In the ekpyrotic model, the smoothing happens during the slow, gentle approach of the branes, making a separate, ad hoc period of inflation unnecessary. The cycle doesn't end there. After the collision and the subsequent expansion of our universe, gravity will eventually take over. Over trillions of years, the expansion will slow, halt, and reverse, pulling all matter and energy back together. But instead of collapsing into a singularity, the universe's contraction will simply bring our brane closer to its parallel partner once again, setting the stage for another collision and another fiery rebirth. In this vision, what lies beyond is not an end, but an intermission in an eternal, rhythmic dance of creation and destruction, where each universe is a single note in an endless cosmic symphony. As we continue to explore the architecture of the multiverse, we arrive at a theory that provides a concrete, albeit staggering, mathematical foundation for the very idea of a cosmos with variable laws. This is the concept of the cosmic landscape, a vision that emerges directly from the depths of string theory. It proposes that what lies beyond our universe is not just more space, but a veritable archipelago of physical possibilities, a meta-reality of such immense proportions that it dwarfs our observable cosmos into insignificance. In this landscape, the fundamental constants of nature, the strength of gravity, the mass of an electron, the very number of dimensions are not absolute truths etched into the fabric of reality. Instead, they are more like local bylaws, adjustable parameters that can vary from one cosmic island to the next. To understand how such a thing is possible, we need to revisit the core idea of string theory. It suggests that the fundamental building blocks of reality are not point-like particles but unimaginably tiny, vibrating loops of energy. The specific way these strings vibrate determines the properties of the particles they manifest, much like different vibrations of a violin string produce different musical notes. Now, for these vibrations to be mathematically consistent, string theory requires more dimensions than the 3 of space and 1 of time that we experience. It typically needs 10 or 11. The extra dimensions are thought to be compactified or curled up into a fantastically small, complex shape at every point in space. This shape is known as a Calabi-Yau manifold, a multi-dimensional geometric form that is central to the theory, and here is where the landscape opens up. It turns out there is not just one unique way to curl up these extra dimensions. There are an astronomical number of possible stable configurations for a Calabi-Yau manifold, each with a distinct topology, different numbers of holes, twists, and folds. The specific geometry of this hidden, compactified space directly influences the way strings can vibrate within our familiar 4-dimensional spacetime. A slight change in the shape of this manifold would alter the vibrational patterns of the strings, which in turn would change the masses of particles, the strengths of forces, and even the effective number of dimensions we perceive. In essence, each possible configuration of the Calabi-Yau manifold corresponds to a different set of laws of physics for a potential universe. When physicists began to calculate just how many of these stable configurations might exist, the number they arrived at was beyond human comprehension. The estimate is often cited as 10 to the power of 500. To grasp the scale of this number, consider that the total number of atoms in our entire observable universe is estimated to be around 10 to the power of 80. The number of possible vacuum states in the string theory landscape is so vast that it makes the number of atoms in our cosmos seem infinitesimally small by comparison. This is the cosmic landscape, a theoretical space of 10 to the 500 distinct, self-consistent universes, each with its own unique physical laws. Our universe, with its specific, life-permitting constants, is simply one tiny point in this inconceivably vast terrain. This provides a powerful, if speculative, explanation for the mysterious fine-tuning of our cosmos. Why does the universe seem so perfectly calibrated for the emergence of life? If the cosmological constant were slightly larger, the universe would have ripped itself apart before galaxies could form. If the strong nuclear force were a fraction weaker, atomic nuclei would never have coalesced. In the context of the landscape, the answer is statistical. With 10 to the 500 possibilities, it is virtually inevitable that a small subset of universes will, by pure chance, have the right combination of constants to allow for stars, planets, and life. We exist in one of these rare, hospitable pockets not because of design, but simply because we could not have arisen anywhere else. This is the anthropic principle applied to a near-infinite array of physical realities. Yet the cosmic landscape theory is not without its profound controversies. For some, a theory that predicts 10 to the 500 possible outcomes is not a triumph of explanation but a failure. Critics argue that if a theory can accommodate almost any set of physical laws, then it becomes effectively unfalsifiable. It can explain everything and therefore predicts nothing specific about our world. It can seem like a retreat from the traditional goal of physics, which is to find a unique, fundamental theory that necessarily gives rise to the universe we see. Furthermore, the concept raises a deep philosophical question about the nature of science itself. If our laws are just a random draw from a cosmic lottery, can we ever hope to understand the true, fundamental principles underlying all of reality? Or are we merely describing the local rules of our particular cosmic neighborhood? The landscape suggests that what lies beyond is not a single, elegant equation, but an endless, branching tree of potentialities, leaving us to wonder if the ultimate truth of existence is unity or an infinite and eternal diversity. Now, let's turn our attention from the vast cosmic landscape to a more specific and explosive possibility, one that connects the fate of individual stars to the birth of entire universes. We've all heard of black holes, those cosmic traps from which not even light can escape. But what if every black hole has a secret exit? This is the white hole hypothesis, a theory that suggests the ultimate destiny of matter falling into a black hole isn't oblivion, but rebirth in a brand new reality. In this stunning vision, what lies beyond our universe could be the erupting fountain of a white hole, and our entire cosmos might be the offspring of such an event in a grand ancestral universe. To understand this, we need to explore the mathematics that first hinted at this cosmic duality. When Carl Schwarzschild found the first solution to Einstein's equations of general relativity describing a non-rotating black hole, the math revealed something peculiar. The solution actually described two connected regions, the black hole itself and a theoretical opposite called a white hole. While a black hole is defined by an event horizon that nothing can cross from the outside in, a white hole would have an event horizon that nothing can cross from the inside out. It would be a region of space-time that eternally expels matter and energy, a cosmic geyser of infinite power. For decades, physicists largely considered white holes to be mathematical curiosities, unlikely to exist in the real world because they seem to violate the second law of thermodynamics by spewing out order from nowhere. However, the theory gained new life when physicists considered what might lie at the very center of a black hole. General relativity predicts that collapsing matter is crushed into an infinitely dense point called a singularity, a place where the laws of physics as we know them break down completely. This is deeply unsatisfying, and many scientists believe a theory of quantum gravity is needed to explain what truly happens. One compelling idea is that the immense gravitational pressure at the singularity doesn't lead to infinite density, but instead triggers a quantum bounce. In this scenario, the collapsing matter reaches a point of maximum density and then rebounds, exploding outward into a new region of space-time. From the perspective of an outside observer in the parent universe, this event would look exactly like a white hole, violently spewing out all the material that originally fell in. This leads to the breathtaking core of the hypothesis. That new region of space-time created by the bounce wouldn't be a part of our universe. The expansion from the white hole would create an entirely new, self-contained cosmos, with its own dimensions and physical laws potentially different from its parent. The event horizon of the original black hole would then act as a one-way bridge, a cosmic umbilical cord connecting the two universes. This means that every black hole in our universe could be a portal to a new embryonic universe, and by extension, our own Big Bang might have been the white hole eruption of a black hole in a much larger, older universe. Imagine our cosmos as a leaf on a vast fractal tree of reality. Each black hole that forms in a universe is like a seed, which then germinates and grows into a new branch, a whole new universe. Our universe, with its billions of galaxies, each containing billions of stars and potentially even more black holes, would itself be a prolific seed producer, giving birth to an incomprehensible number of daughter universes. This creates a cosmic family tree, a multiverse not of parallel bubbles, but of genealogically connected realities, each born from a singular cataclysmic event within another. This theory offers a uniquely elegant solution to the mystery of what caused the Big Bang. Instead of a singularity appearing from nothing, the Big Bang was the moment our universe was born from the white hole of a black hole in a parent cosmos. It also provides a potential mechanism for the evolution of physical laws. If the specific conditions of the black hole's formation and collapse influence the properties of the new universe, then universes that produce more black holes, and thus more offspring, would come to dominate the multiverse. This introduces a form of cosmic natural selection, where universes fit for producing black holes are the ones that proliferate, potentially explaining why our universe seems so adept at creating them. While still highly speculative and facing challenges, such as explaining the observed homogeneity of our universe, the white hole hypothesis paints a profoundly interconnected picture of existence, suggesting that the darkest objects in our sky may not be endpoints but cosmic wombs. This idea that black holes might be cosmic nurseries naturally leads to a related and equally mind-bending possibility. What if the tables were turned and our entire cosmos wasn't the parent but the child? What if the universe we inhabit is itself nestled within the interior of an unimaginably vast black hole? This is the startling proposal that our observable universe, with all its hundreds of billions of galaxies, might share key characteristics with the very objects it contains. In this view, the boundary of our cosmic horizon, the limit of what we can see, isn't just a limit of observation. It could be a physical boundary, an event horizon separating our reality from a larger meta-universe. To see how this could be possible, we need to look at some surprising mathematical similarities. The defining feature of a black hole is its event horizon, the point of no return. The size of this horizon, known as the Schwarzschild radius, is directly proportional to the mass of the black hole. Now, let's perform a thought experiment. Imagine you could gather all the mass and energy contained within our observable universe and calculate what size black hole it would form. The result is a specific radius. Astonishingly, the actual estimated radius of our observable universe is remarkably close to this calculated Schwarzschild radius for its total mass energy content. This numerical coincidence is provocative. It suggests that if you were to somehow squeeze all the matter in our cosmos into a region small enough, it would naturally form a black hole with a horizon the size of our universe. But the parallels go deeper than a simple size comparison. Consider the ultimate fate of an object falling into a black hole. From the perspective of an outside observer, due to the extreme effects of gravity on time known as time dilation, the object appears to slow down infinitely as it approaches the event horizon, never quite crossing it. However, from the perspective of the object itself, it crosses the horizon in a finite amount of time and continues inward. Now, apply this to the Big Bang. From our perspective inside the universe, time began at the Big Bang, a singular point of infinite density. But what if, from an outside perspective in a parent universe, our Big Bang was the moment an immense amount of energy crossed an event horizon? Our entire cosmic history, from the first second to the present day, could be unfolding on the inside of that horizon, much like the journey of infalling matter within a black hole. This leads to the captivating image of a cosmic Russian nesting doll. Our universe, with its own galaxies containing black holes, could be nestled inside a black hole that exists within a much larger meta-universe. And that meta-universe might itself be inside an even larger black hole in a hierarchy that continues indefinitely. This isn't just a fanciful analogy. It emerges as a potential solution within certain theories of quantum gravity. When physicists try to model what happens at the core of a black hole, where general relativity predicts a singularity, some models suggest the collapsing matter rebounds, creating a new, expanding space-time region. This new region would be causally disconnected from the parent universe, precisely what we observe our universe to be. The implications of this theory are profound. First, it offers a potential explanation for why our universe appears to be so uniform on the largest scales. The interior of a black hole, after the initial chaos of its formation, might naturally settle into a state of high homogeneity, similar to how our universe appears in the cosmic microwave background. Second, it could explain the initial low entropy state that so puzzled us with the Boltzmann brane paradox. The formation of a black hole is an event that creates a large amount of order. Our universe's beginning with low entropy might simply reflect its origin as the interior of a newly formed black hole in a larger cosmos. Perhaps the most staggering implication is that it redefines the concept of outside. If we are inside a black hole, then the space beyond our cosmic horizon is not more of our own universe that we simply cannot see due to the finite speed of light. Instead, it is a fundamentally different realm, part of the exterior universe that contains our cosmic prison. The galaxies we see at the very edge of our observable limit would be those closest to our event horizon, their light taking almost the entire age of the universe to reach us. What lies beyond that horizon is the gravitational well of the parent black hole, and ultimately the entirety of the meta-universe it calls home. This vision transforms our cosmos from a lone island in a void into a single chamber within an immeasurably grander structure, suggesting that every black hole we see in our night sky might be a window into a completely new cosmic reality. While many theories about the cosmos grapple with dramatic beginnings and endings, our next concept presents a vision of remarkable constancy. It's a return to an old idea with a modern twist, a theory that suggests the universe has no ultimate origin and faces no final fate, but simply is in a state of perpetual renewal. This is the steady-state theory, or more accurately, its contemporary revisions, which propose that what lies beyond our observable horizon is not a wall or a boundary, but more of the same, an infinite, eternal cosmos that is forever creating itself. The original steady-state model was a powerful competitor to the Big Bang theory in the mid-20th century. Its core principle, championed by astronomers like Fred Hoyle, Hermann Bondi, and Thomas Gould, was the perfect cosmological principle. This principle stated that the universe is not only uniform in space, looking roughly the same in every direction, but also uniform in time. It should look essentially the same to any observer at any point in history. This presented a direct challenge to the Big Bang, which implied a dynamic universe with a definite starting point that was vastly different from its current state. To maintain this eternal sameness in the face of the observed expansion of the universe, the steady-state theory proposed a radical idea: the continuous creation of new matter. As galaxies drifted apart due to cosmic expansion, tiny amounts of new hydrogen atoms would spontaneously pop into existence in the voids between them, just enough to maintain a constant average density over time. This new matter would eventually coalesce into new galaxies, replacing the old ones that moved away, ensuring the overall appearance of the cosmos never changed. For a time, this elegant idea held sway, but it eventually lost ground to the overwhelming evidence for the Big Bang. The discovery of the cosmic microwave background radiation in 1965 was a decisive blow. This faint glow filling all of space was exactly the predicted remnant of a hot, dense beginning, a relic the steady-state theory struggled to explain. Furthermore, observations of distant quasars showed that the universe was different in the past. It evolved, contradicting the perfect cosmological principle. As a result, the classical steady-state model was relegated to the history books of cosmology. Yet, like a cosmic phoenix, the core idea has found new life in modern speculative physics. Today's revised versions of the steady-state concept no longer cling to strict timelessness, but they explore the fascinating possibility that the mechanism of continuous creation might still be at work on a much grander scale. In these models, the expansion of the universe and the creation of new matter are intertwined processes. What lies beyond our observable universe, according to this view, are regions where this process is ongoing. As space stretches, new matter and energy are generated to fill the void, not from a singular past event, but as an intrinsic property of space-time itself. Our observable cosmos would then be just a local sample of an infinite, eternal reality that has no true beginning and no end. This revised picture offers a compelling alternative to the heat-death scenario. Instead of a universe slowly fading into a cold, dark, and empty state, a steady-state cosmos would be forever active. New stars would always be forming from the newly created material, new galaxies would assemble, and the cycle of stellar birth and death would continue indefinitely. The universe would be ageless, with no need for a definitive start. The question, what happened before the Big Bang, becomes meaningless because there was no Big Bang, just an endless, ongoing process of creation and renewal. One of the most significant challenges for any modern steady-state theory is explaining the observed evidence for a hot, dense beginning like the cosmic microwave background. Proponents have proposed alternative explanations, suggesting this background radiation could be the scattered light from an infinite population of stars in an eternal universe, or the result of other processes that mimic a primordial fireball. While these explanations are not part of the mainstream consensus, they highlight the theory's enduring appeal. It presents a universe that is fundamentally stable and self-sustaining. It removes the existential dread of a definitive end and the metaphysical puzzle of an absolute beginning, offering a vision of existence as an everlasting, dynamic equilibrium. In this eternal cosmos, what lies beyond is simply more universe, forever being woven into existence from the fabric of space-time itself. From the idea of an eternal, self-sustaining cosmos, we now turn to a theory that is perhaps the most minimalist and philosophically challenging of all. It strips away every layer of complexity to ask a deceptively simple question: What if the default state of existence is not existence at all? This is the null universe concept, a perspective that suggests reality is fundamentally rooted in absolute nothingness, and the vibrant, complex universe we perceive is nothing more than a fleeting, statistical anomaly in an infinite and eternal void. In this view, what lies beyond our universe is not a multiverse, not a higher dimension, but the true, foundational state of affairs, pure non-existence. To truly grasp this idea, we must first try to understand what nothing really means. We often use the word to describe an empty box or the vacuum of space, but these are not true nothingness. An empty box exists within space and time. The vacuum of space, as quantum physics tells us, is a seething foam of virtual particles popping in and out of existence, governed by fundamental fields and laws. The nothingness proposed by the null universe concept is far more absolute. It is the absence of everything: no space, no time, no matter, no energy, not even the potential for such things. It is a state where the very concepts of where, when, and what are completely meaningless. This is not a void within a container, it is the absence of the container itself. How, then, can a universe arise from such a perfect null state? The answer lies in the bizarre world of quantum mechanics, which governs reality on the smallest scales. One of its core principles is uncertainty. Particles don't have definite properties until they are measured, instead existing in a haze of probability. This uncertainty even applies to the energy content of a system. It is possible, according to quantum rules, for a system to fluctuate briefly into a state of higher or lower energy. In our universe, we see this in the constant appearance and disappearance of virtual particle pairs in otherwise empty space. The null universe concept takes this idea to its ultimate extreme. It proposes that the ultimate system is the state of absolute nothingness, and that even this perfect void is subject to quantum uncertainty. Given an infinite amount of time, or more accurately, in a realm where time itself has no meaning, a fluctuation could occur. A bubble of something could spontaneously emerge from the nothing. A universe could wink into existence simply because the probabilistic laws of quantum mechanics do not strictly forbid it, even if the probability is astronomically small. This leads to a staggering implication about our own existence. If this concept is correct, then our entire cosmos, with its 13.8 billion years of history and its hundreds of billions of galaxies, is that incredibly rare fluctuation. We are a cosmic accident, a temporary deviation from the norm of non-existence. The laws of physics we work so hard to understand are not fundamental truths etched into the fabric of reality. They are simply the local, temporary rules that govern this particular fluctuation. And just as the fluctuation began, it will likely end. The ultimate fate of our universe in this picture is not a heat death or a big crunch, but a simple fading back into the null state from which it came. All structure, all energy, all consciousness would simply cease to be, reabsorbed into the absolute nothingness that is the true and eternal baseline of reality. This theory presents a profound philosophical challenge. It seems to answer the ancient question of why there is something rather than nothing by stating that most of the time there is nothing. Our existence is a brief and fortunate exception. Yet it also raises a new and perhaps even more difficult question. How can the laws of quantum mechanics, which allow for such a fluctuation, exist in a state of true nothingness? If there is no space, no time, and no fields, what is there to fluctuate? Proponents might argue that the potential for quantum events is more fundamental than existence itself, a primitive logical possibility that requires no pre-existing substrate. Critics, however, see this as a major weakness, arguing that the theory simply pushes the problem back one step without truly solving it. Despite these challenges, the null universe concept remains a powerful and humbling perspective. It suggests that the grand story of the cosmos is not an epic of creation and destiny, but a fleeting whisper in an endless, silent night, a temporary stirring in a sea of perpetual stillness. Closely related to the idea of a null universe, but with a crucial and fascinating twist, is the theory that our cosmos is a quantum fluctuation. This concept doesn't require a state of absolute nothingness, but instead posits that our universe emerged from a pre-existing, albeit strange, foundation, the primordial quantum vacuum. What lies beyond, in this view, is not a perfect void, but an eternal, seething sea of potentiality, a foaming ocean of energy where entire universes can spontaneously blink into and out of existence. To understand this, we need to refine our idea of a vacuum. In everyday language, a vacuum is just empty space. But in quantum field theory, the framework that combines quantum mechanics and special relativity, the vacuum is anything but empty. It is the lowest possible energy state of a field, but it is still alive with activity. Due to the Heisenberg uncertainty principle, which forbids perfect stillness at the quantum level, this vacuum is constantly fluctuating. Pairs of virtual particles, one matter, one antimatter, spontaneously pop into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning the energy. This isn't just theoretical, it's a verified phenomenon with observable effects like the Casimir effect, where two metal plates placed extremely close together in a vacuum feel a slight pressure from the particle activity outside them. The quantum fluctuation theory takes this well-established microscopic process and scales it up to a literally cosmic degree. It proposes that our entire universe began as one of these random fluctuations, but on an unimaginable scale. In the eternal, metastable quantum vacuum, a fluctuation of sufficient energy could have occurred, tunneling from nothingness into somethingness. This wouldn't be the creation of a few particles, but the spontaneous genesis of an entire spacetime continuum, complete with all the energy that would eventually become galaxies, stars, and us. The Big Bang in this scenario was the moment this bubble of spacetime began its rapid expansion. The immense positive energy of all the matter in the universe would be perfectly balanced by the negative gravitational potential energy of all that matter pulling on itself, resulting in a net energy of zero. In a very real sense, the universe could be the ultimate free lunch, a fluctuation that required no net input of energy because its total energy sums to nothing. This idea was powerfully championed by physicists like Edward Tryon, who, in the 1970s, suggested that our universe might simply be a large-scale version of a virtual particle pair. Just as those particles appear without breaking any fundamental conservation laws, so too could our cosmos. The primordial quantum vacuum from which we emerged is then what truly lies beyond our cosmic horizon. It is a timeless, spaceless arena, or perhaps a background state, that is not a void in the classical sense, but a realm of pure potential governed by quantum probability. Within this sea, other universes are constantly forming, each with its own random set of physical constants and laws. Most of these universes would be stillborn, collapsing back into the vacuum almost immediately. Others might expand for a brief moment before fading away. A rare few, like ours, would have just the right conditions to undergo a period of rapid inflation, stabilizing them and allowing them to grow to an enormous size, eventually giving rise to complexity and life. This vision paints a picture of a multiverse that is far more frenetic and probabilistic than the orderly bubble universes of eternal inflation. It's a cosmos where existence is the exception, not the rule, and where the birth of a universe is a commonplace, if ephemeral, event. The profound implication is that the quantum laws that allow for such fluctuations are more fundamental than the universe itself. They are the true bedrock of reality, and our universe is merely a single, particularly successful manifestation of those deeper principles. This provides another compelling answer to the fine-tuning problem. In an infinite quantum vacuum, every possible universe will eventually fluctuate into existence. We find ourselves in one that can support us not because it was designed, but because the vast majority of universes are inhospitable and we simply cannot exist within them. Our presence here is a form of observational selection bias. Of course, this theory faces its own set of deep questions. What is the nature of this primordial quantum vacuum? Does it exist within some meta-time, or is the concept of time itself born with each new universe? If the vacuum has laws, who or what wrote them? These are the frontiers of current physics where our understanding begins to blur into philosophy. Yet the quantum fluctuation theory remains one of the most elegant and scientifically grounded attempts to explain the origin of everything from almost nothing, suggesting that the ultimate creative force in the cosmos is not a divine hand, but the restless, probabilistic churn of the quantum world. Now we shift our focus from the birth of entire cosmoses to a theory that unfolds the multiverse not across space, but within the very fabric of reality itself, one quantum event at a time. This is the many worlds interpretation of quantum mechanics, and it proposes a vision of existence so prolific that it makes every other multiverse theory seem conservative. It suggests that what lies beyond our universe is not a distant collection of alien realms, but an infinite, ever-branching tree of realities sprouting from every single moment, where every possible outcome of every quantum event is not just a possibility but an actuality. To understand this astonishing idea, we first need to grapple with the central weirdness of quantum mechanics, the physics of the very small. At this level, particles don't behave like tiny billiard balls. Instead, they exist in a blurred state of potentiality called a superposition. A famous example is Schrödinger's cat, a thought experiment where a cat in a box is simultaneously alive and dead until someone opens the box to look, at which point its state becomes definite. The standard explanation, the Copenhagen interpretation, says that the act of observation forces the particle or the cat to choose a single state from its menu of possibilities. But this raises a deep question. What is so special about observation? Why should consciousness have the power to collapse probability into reality? The many worlds interpretation proposed by physicist Hugh Everett in the 1950s offers a radical and elegant solution. It says the collapse never happens, there is no choice. Instead, when a quantum system faces multiple possibilities, the entire universe splits or branches to accommodate every single outcome. In the case of Schrödinger's cat, at the moment the quantum trigger is activated, the universe divides. In one branch, an observer opens the box to find a living cat. In another, completely separate branch, an identical observer opens the box to find a dead cat. Both events are equally real. Both observers are conscious, each convinced that their outcome was the only one that occurred. The branching is not a physical tearing of space-time, but a decoherence of quantum possibilities into separate, non-communicating timelines. This process is not reserved for dramatic laboratory experiments. It is happening constantly at an unimaginable rate. Every time an electron has a choice of paths to take, every time a photon is reflected or transmitted, the universe branches. Every time you make a decision, even a seemingly insignificant one, like whether to turn left or right on your walk, the quantum processes in your brain that underlie that thought are subject to probability, and thus the universe splits. In one world, you turn left, in another, you turn right, and each version of you continues down a timeline that diverges further with every subsequent quantum event. The implication is that there is a universe where you never watched this video, a universe where every lottery ticket you ever bought was a winner, and a universe where the laws of physics themselves took a different turn during the Big Bang. So, what lies beyond our cosmic horizon in this view? The answer is both simple and overwhelming. The beyond is simply the rest of the infinite ensemble of worlds. Our observable universe is just one branch on an infinitely complex, ever-growing tree of reality. The galaxies we see at the edge of our vision are not bordering an empty void or a different cosmic bubble. They are simply the part of our specific branch that we can see. Beyond them, space continues, but it is a space that is also occupied by an infinite number of slightly different versions of our own universe, and an even vaster number of radically different ones. The many worlds interpretation transforms the cosmos from a single narrative into a never-ending, parallel publication of every story that can possibly be told. This theory removes the need for a mysterious observer-induced collapse and places quantum mechanics on a deterministic footing. The evolution of the wave function, which describes all possibilities, is continuous and smooth. The appearance of randomness in our world is just an illusion, a consequence of us being trapped on a single branch, unaware of our countless parallel selves. While profoundly elegant, the theory faces its own challenges, primarily its staggering ontological extravagance. It asks us to believe in an infinite number of unobservable universes to explain the quirks of our own. Furthermore, it's difficult to test as by definition we are confined to our own branch. Yet, for many physicists, the sheer logical consistency of many worlds makes it a compelling answer to the quantum riddle, suggesting that the ultimate reality is a multiverse of breathtaking richness where every possibility is not just dreamed but lived. If the many worlds interpretation suggests reality is an ever-branching computation, our next theory asks what is actually being computed. We arrive at a concept that pushes the idea of a digital cosmos even further, proposing that information itself is the most fundamental substance of existence. This is the theory of the universe as an information system, a perspective known as digital physics or the it-from-bit doctrine. It suggests that what we perceive as matter, energy, and even the laws of physics are not the primary reality but secondary manifestations. The true bedrock of the cosmos is data, and what lies beyond our universe might be the ultimate processor or the source code governing this cosmic computation. This revolutionary idea was profoundly articulated by the visionary physicist John Archibald Wheeler. He coined the phrase "it from bit" to capture the essence of this concept. The it refers to every particle, every force field, everything that makes up our physical world. The bit is the binary unit of information, a simple yes or no, 1 or 0 distinction. Wheeler's radical proposal was that every facet of the physical world ultimately derives its existence from binary choices made in response to yes or no questions. At the most fundamental level, the universe is not made of tiny strings or point-like particles, but of bits of information. The solidity of a rock, the heat of a star, and the flow of time itself are all emergent properties arising from an underlying, ceaseless information processing event. How could this possibly work? A powerful analogy is to think of a modern video game. On your screen, you see a rich, three-dimensional world with realistic physics. Gravity affects objects, water flows, and characters interact. But this world is not fundamentally made of dirt, water, or flesh. It is made of code. The mountains and rivers are just graphical representations of data stored in the computer's memory. The laws of physics in the game, how high a character can jump, how fast a car can go, are not real laws of nature. They are the rules of the program. The digital physics perspective argues our universe operates on the same principle. The atoms in your body are incredibly sophisticated patterns of information. The force of gravity is not a fundamental force pulling matter together, but a consequence of how information about mass and distance is processed and related within the cosmic computer. This view finds surprising support in some of the deepest mysteries of modern physics. Take the phenomenon of quantum entanglement, which Einstein called spooky action at a distance. When two particles become entangled, measuring the state of one instantly determines the state of the other, no matter how far apart they are. This seems to violate the cosmic speed limit set by light. But from an information-based perspective, this spookiness might make perfect sense. If the two particles are not separate objects communicating, but are instead linked by a common underlying information state, then there is no signal traveling through space. The correlation is instantaneous because it is written into the foundational code of reality from the start. The outcome was always part of a single, coherent data structure. Furthermore, this theory offers a fresh perspective on the nature of black holes, which we've seen are central to so many cosmic theories. The holographic principle, which suggests all the information about a three-dimensional volume can be encoded on a two-dimensional surface, fits beautifully within an information-based cosmos. A black hole's event horizon could be seen as a cosmic hard drive, with its surface area determining its maximum information storage capacity. The infamous black hole information paradox, the question of what happens to information that falls into a black hole, becomes a critical issue about data conservation in the universe's operating system. So, what lies beyond our universe in this digital metaphysics? The answer could be as straightforward as it is staggering. Beyond the horizon of our observable cosmos might not be more space, but the hardware on which our universe is running. Our entire reality, from the Big Bang to the present day, could be a simulation on a cosmic-scale computer in a higher-level reality. Alternatively, and perhaps even more mind-bendingly, the universe might not be a simulation running on an external computer, but a self-contained, self-computing entity. In this view, the cosmos is the computer, the laws of physics are the algorithms it is executing, and the unfolding history of the universe is the result of that ongoing computation. The question, what is the universe computing, might have a recursive answer: it is computing itself. This leads to a profound implication about the nature of consciousness. If our minds are also patterns of information processing within this cosmic computer, then our awareness and our quest for understanding are not just byproducts of the computation. They are an integral part of the process itself, the universe becoming conscious of its own code. If the idea of parallel universes sounds like science fiction, wait until you hear about the possibility of a parallel reality interwoven with our own, made of matter so elusive it might as well be a ghost. This brings us to a theory deeply rooted in the quest to unify the forces of nature, the supersymmetric universe. At its heart, supersymmetry, or SUSY for short, is a beautiful mathematical proposition that aims to fix a glaring asymmetry in our current map of particle physics, the Standard Model. This model categorizes all known fundamental particles into two distinct families: the fermions, which are the building blocks of matter like quarks and electrons, and the bosons, which are the force carriers like the photon for electromagnetism. Supersymmetry proposes a profound and elegant link between these two families, suggesting that for every known fermion, there should be a supersymmetric boson partner, and for every known boson, a supersymmetric fermion partner. These hypothetical particles are often given playful names, adding a S to fermions and an ino to bosons. So, the electron would have a partner called the selectron, a boson. The quark would have a squark. Conversely, the photon, a boson, would have a fermion partner called the photino. This symmetry is more than just a neat organizational trick. It solves several major theoretical problems in one stroke. For instance, it provides a compelling candidate for the mysterious dark matter that makes up about 85% of the matter in the cosmos. The lightest supersymmetric particle, often thought to be the neutralino, would be stable, electrically neutral, and would barely interact with ordinary matter, ticking all the boxes for what dark matter is believed to be. Furthermore, supersymmetry helps unify the fundamental forces at high energies, suggesting that electromagnetism, the weak nuclear force, and the strong nuclear force were all one and the same force in the early universe. But the implications for what lies beyond our universe are even more staggering. If these superpartners exist, why haven't we detected them? One compelling answer is that the symmetry between particles and their superpartners is broken. This means that while the elegant mathematical connection exists, the superpartners are incredibly massive, far heavier than their ordinary counterparts. This is where the theory truly expands our horizons. It's possible that this supersymmetry breaking was not uniform across the cosmos. What if, in the fiery moments following the Big Bang, different regions of spacetime underwent this symmetry breaking in different ways? In our local cosmic neighborhood, the specific conditions led to the superpartners becoming immensely heavy, effectively pushing them into a realm beyond our current observational reach. This opens the door to a breathtaking possibility, a hidden sector of the universe. In this scenario, what we call the universe, with all its stars, galaxies, and everything we can see and touch, is just one sector, one particular manifestation of the underlying physics. Beyond our perceptual and instrumental grasp could lie a shadow universe, a cosmos dominated by supersymmetric particles. This shadow realm would have its own version of matter, its own set of forces, and potentially even its own complex structures, all built from these superpartners. Because these particles interact so feebly with our own, this entire parallel reality would be coexisting with us, overlaying the same space, yet remaining almost entirely invisible and undetectable. It would be like living in a world of sound, completely unaware that a world of light exists in the exact same location, only perceivable to those with the right senses. The means of interaction between our sector and this hidden one would be incredibly subtle, likely occurring only through the weakest of all forces, gravity. This means that the only way we might feel the presence of this shadow universe is through its gravitational influence. This provides an elegant and deeply physical explanation for the dark matter mystery. The ghostly halo of dark matter that surrounds our galaxy and binds clusters of galaxies together might not be a cloud of unknown particles within our sector, but the gravitational shadow cast by an entire, bustling universe of supersymmetric matter existing just alongside our own. We are like ships sailing on an ocean, sensing the presence of a massive underwater continent only by the way it bends the surface of the water, never able to see the continent itself. The search for supersymmetry, then, is not just a hunt for new particles in our accelerators. It is a quest to detect the faintest gravitational echo from a cosmic neighbor we have never seen. A reality so close it is literally all around us, yet separated by a fundamental difference in physical nature. From the idea of a cosmos built on information, we now turn to a theory that places the observer at the very heart of existence, not as a passive recipient of reality, but as its active creator. This is the proposition that the universe is a consciousness projection, a concept that challenges the bedrock assumption of modern science, that a physical, objective world exists independently of us. This perspective, known as philosophical idealism, flips the standard materialist view on its head. It suggests that mind or consciousness is not a late-arriving product of complex brains in a material universe, but is in fact the primary substance of reality. What we perceive as the physical cosmos, the stars, the planets, the very fabric of spacetime is a grand projection, a manifestation emerging from a deeper, universal mind. To understand this radical shift, consider the nature of your own experience. Everything you know about the world comes to you through your senses. The color red, the sound of music, the feeling of warmth. These are all qualia, subjective experiences happening within your consciousness. You have no direct access to a world out there. You only have the model of it that your brain constructs from sensory data. Idealism takes this observation to its logical extreme. It argues that since all we can ever know is the content of our own consciousness, it is more parsimonious to assume that consciousness itself is the fundamental reality. The solid, external world is a consistent and shared dream within a universal consciousness, rather than a dream being an internal and private copy of an external world. This is not a new idea. It has deep roots in Eastern philosophies like Advaita Vedanta, which speaks of Brahman as the ultimate non-dual reality, of which the perceived world is a manifestation or maya, often translated as illusion. In the West, the 18th century philosopher George Berkeley argued that to be is to be perceived, that objects only exist in the mind of a perceiver. The modern version of this theory often engages with the mysteries of quantum mechanics, which seems to lend some credence to the role of the observer. The infamous quantum measurement problem, where a particle's definite properties seem to crystallize only upon observation, has led some physicists like John von Neumann and Eugene Wigner to speculate that consciousness plays a crucial role in collapsing the wave function, bringing potentiality into actuality. So, what would lie beyond our observable universe according to this view? The answer is both simple and profound. Beyond the farthest galaxy and the cosmic microwave background radiation lies not more physical space, but the source of the projection itself, the universal consciousness. This would be a realm of pure mind, without form, without substance, but containing the potential for all forms and all substances. Our universe in its entirety would be a thought within this vast mind, a complex, self-consistent idea that has been given apparent substance through the act of observation. The laws of physics would not be discovered rules of an external reality, but rather the intrinsic grammar of this cosmic consciousness, the logical structure by which it organizes its own thoughts. This leads to a breathtaking implication about our own nature. If the universe is a projection of a universal mind, then our individual consciousnesses are not isolated products of biology. Instead, they are localized expressions, focal points, or whirlpools within the greater ocean of universal consciousness. We are not separate from the source of reality, we are part of it. Our sense of individuality is an illusion created by the specific, limited perspective of our biological apparatus. This idea resonates with mystical experiences of unity reported across cultures, where individuals feel a dissolution of the self and a merging with a greater, all-encompassing awareness. In this light, the entire scientific endeavor is not the exploration of an external world, but the process of universal consciousness exploring the intricate details of its own creation. Of course, this theory faces significant challenges from a scientific standpoint. The most obvious is the so-called dinosaur problem. If a tree falls in the forest and no one is around to hear it, does it make a sound? In a strict idealist framework, without a conscious observer, does the forest even exist? Proponents might answer that the universal consciousness itself is the perpetual observer, sustaining the universe in a state of consistent existence. Another major challenge is explaining the stunning consistency of the physical world. Why do we all agree on the laws of physics? Idealism would suggest that we are all participating in the same shared mental construct, a collective dream with consistent rules that are enforced by the foundational nature of the universal mind itself. While this theory may currently lie beyond the reach of empirical falsification, it offers a deeply meaningful and coherent vision of reality, one that places sentience and experience at the absolute center of the cosmic story, suggesting that the ultimate frontier is not a place in space, but the very nature of mind itself. This brings us to a particularly dynamic and influential vision of the multiverse, one that provides a specific, physics-based mechanism for how an endless array of universes could actually come into being. We've already touched upon the general idea of a multiverse, but the eternal inflation scenario details the engine that could drive such a prolific creation. It suggests that what lies beyond our cosmic horizon is not a quiet emptiness, but a frenzied, hyper-expanding meta-reality, a cosmic factory floor where new universes are constantly being manufactured. The story begins with our own universe's earliest moments. The leading theory for the Big Bang includes a brief period called cosmic inflation, a fraction of a second after the beginning where the universe expanded at a rate far exceeding the speed of light. This rapid stretching elegantly explains several key features of our cosmos: such as why it appears so uniform on large scales and why its geometry is so flat. According to the Standard Model, this inflationary period started, smoothed things out, and then stopped, allowing the more sedate expansion we see today to take over and for particles to form. But what if, for most of reality, inflation never stops? This is the core premise of eternal inflation. Imagine a vast, primordial landscape of energy, often called the inflaton field. Think of this field not as a flat plain, but as a rugged, mountainous terrain. The valleys in this landscape represent low-energy states where inflation can come to an end. The high peaks and plateaus represent high-energy states where the driving force for hyper-expansion is incredibly strong. Now picture a ball resting high up on a plateau. This ball represents a patch of space-time. In this high-energy state, inflation is raging, causing that patch of space to expand at an unbelievable rate. But due to quantum fluctuations, tiny random jitters, the ball can randomly tumble down into a valley. When that happens in a local region, inflation stops for that specific area. The immense energy of the inflaton field is released, flooding that region with particles and radiation, a process we would recognize as a Big Bang. This localized region becomes a stable, low-energy bubble universe like our own, embedded within the still inflating high-energy background. But here's where the eternal part takes hold. While one region tumbles into a valley and stops inflating, the vast majority of the space surrounding it is still on the high plateau, continuing to inflate at an exponential rate. This means the volume of the still inflating background space grows much, much faster than the bubbles that form within it. For every one bubble universe that forms, the inflating background creates enough new space for 1 billion more bubbles to eventually form. This process is self-perpetuating and, according to the math, can never truly come to an end. It is eternal. What lies beyond our bubble, then, is this ever-growing, chaotic sea of hyper-expanding spacetime, a multiverse background that is continuously giving birth to new, isolated bubble universes. The implications of this are staggering. Each of these bubble universes forms with its own random local properties, determined by the specific valley its inflaton field settled into. This means each bubble can have a different set of physical constants, a different number of dimensions, and different fundamental laws. Some bubbles might collapse instantly. Others might expand into vast, barren emptiness. A rare few, like ours, will have just the right combination of laws to allow for galaxies, stars, and life. This provides a powerful, natural explanation for the apparent fine-tuning of our universe without invoking chance or design. In an eternally inflating multiverse that produces every possible type of universe, it's no surprise that we find ourselves in one that can support our existence. This scenario also presents a fascinating picture of our cosmic neighborhood. We are living inside one of these stable bubbles. The boundary of our observable universe is not the edge of our bubble. It's simply the limit of how far light has traveled since our local Big Bang. Our bubble universe is likely much, much larger than what we can see, and beyond its true boundary lies the inflating background. We can never see another bubble universe or travel to one because the space between our bubble and any other is inflating faster than light. Any other bubble is receding from us at an impossible speed, forever isolated. We are cosmic islands in a rapidly rising sea, forever cut off from our neighbors, yet part of an unimaginably vast and creative archipelago of realities. The eternal inflation scenario transforms the question of what lies beyond from a query about empty space into a statement about infinite generative potential, a cosmos that is fundamentally and forever fertile. Now, let's journey into one of the most visually captivating ideas about the nature of reality, a concept that suggests our entire cosmos might be just a surface-level phenomenon. Imagine for a moment that everything you have ever experienced, the depth of a room, the arc of a thrown ball, the passage of time, is merely a shadow. Not a metaphor, but a literal shadow, a low-dimensional projection of a reality that exists in more dimensions than we can perceive. This is the profound proposal that our universe is a higher dimensional object, a notion that stretches the limits of our imagination and could potentially unlock the deepest secrets of physics. To grasp this, we can use a classic analogy. Consider a flat, two-dimensional world like the surface of a pond. Beings living in this flatland would have no concept of up or down. They can only move forward, backward, left, and right. Now, imagine a three-dimensional object like a sphere passing through their two-dimensional plane. To the Flatlanders, this event would be utterly baffling. They wouldn't see a sphere. Instead, they would witness a single point that suddenly appears, grows into an expanding circle, reaches a maximum size, and then shrinks back to a point before vanishing. The true, unified nature of the sphere would be completely hidden from them. They would only perceive a series of changing two-dimensional cross-sections. Their reality is a flat shadow of a richer, higher-dimensional truth. According to this theory, we are in a position strikingly similar to those Flatlanders. We experience a universe with three dimensions of space and one of time. But what if our four-dimensional spacetime is just the surface or membrane of a far grander object existing in 5, 6, or even 10 dimensions? Just as the surface of a sphere is a two-dimensional boundary of a three-dimensional object, our entire cosmic history, every galaxy, every planet, every moment, might be the 3 plus one-dimensional boundary of a higher dimensional shape. What lies beyond our observable universe, then, is not more empty space in our dimensions, but the full, bulk volume of this higher dimensional structure, a realm whose geometry we are fundamentally blind to. This perspective offers a radical new way to think about the fundamental forces that govern our world. Gravity, for instance, has always been the odd one out, incredibly weak compared to the other forces. Why is it so feeble? In the higher dimensional picture, it might not be weak at all. Its strength could simply be diluted because it is not confined to our four-dimensional membrane like the other forces. Perhaps gravity is free to leak out into the extra dimensions, spreading its influence thinly across a much larger volume. From our limited, lower-dimensional perspective, this leakage would make gravity appear exceptionally weak. What we perceive as a fundamental force could be an artifact, a side effect of our constrained point of view within a much larger dimensional arena. This idea finds a powerful home in theories like string theory, which requires extra dimensions for its mathematical consistency. In these frameworks, the particles we see and the forces we feel could be different vibrational modes of tiny, fundamental strings, but their properties are determined by the specific way the extra dimensions are curled up and hidden from our view. The quest for a unified theory of physics then becomes a quest to understand the geometry of this higher dimensional object, the reason why the electron has its specific mass or why the cosmological constant has its precise value might not be random accidents but direct consequences of the shape of the cosmos in these unseen dimensions. We are like sailors on an ocean, trying to understand the nature of water by studying the waves on the surface, completely unaware of the vast depths and complex currents moving beneath us. The true nature of reality may be waiting not at the farthest reaches of space, but in the hidden dimensions folded into the fabric of every single point in our universe. Continuing our exploration of parallel realities, we now encounter one of the most symmetrical and elegant possibilities, a theory that arises not from cosmology but from the fundamental symmetries of particle physics itself. This is the mirror universe concept, a hypothesis proposing that for every particle and every force in our world, there exists a perfect mirror reflection, a hidden twin universe where the most basic rules of nature are subtly reversed. What lies beyond our cosmic horizon in this view could be an almost identical cosmos made of mirror matter, a realm that is both separate from our own and yet intimately connected through the very fabric of physical law. The inspiration for this idea comes from a deep principle in physics known as parity symmetry. For a long time, physicists believed that the laws of nature were perfectly symmetrical. That is, a physical process and its mirror image should be equally possible. Imagine watching a film of two electrons repelling each other. If you played the film in a mirror, you would expect to see the same physics at work. Astonishingly, in the 1950s, this long-held assumption was proven wrong. Qin-Sheng Wu's famous experiment demonstrated that the weak nuclear force which governs radioactive decay violates parity symmetry. In the world of subatomic particles, nature has a definite handedness or chirality. It distinguishes between left and right. This was a profound discovery, showing that the universe is not completely ambidextrous. The mirror universe theory offers a beautiful way to restore this lost symmetry, but on a cosmic scale. It proposes that parity symmetry is indeed a fundamental law, but it operates in a way we hadn't anticipated. Instead of being violated in our universe, the symmetry is preserved by the existence of an entire parallel universe where the handedness of all interactions is flipped. In this mirror world, the weak force would act in the opposite way, making it a universe where left is right and right is left from our perspective. This mirror cosmos would have its own version of particles, mirror electrons, mirror protons, mirror neutrons forming mirror atoms, mirror molecules, and potentially even mirror stars and mirror galaxies. The laws of physics would be identical in form, but their manifestation would be mirrored. The most fascinating implication of this theory is its potential connection to one of the greatest mysteries in modern science, dark matter. We know that about 85% of the matter in the universe is invisible, detectable only through its gravitational pull on galaxies. The mirror universe concept provides a stunningly simple explanation. What if dark matter isn't some exotic, unknown particle? What if it is simply ordinary matter from the mirror universe? In this model, the two universes coexist in the same space, but are largely invisible to each other because the forces that bind mirror matter together do not interact with our matter through electromagnetism or the strong and weak nuclear forces. The only connection between the two worlds is gravity, a force that would affect both types of matter equally. This means the ghostly halo of dark matter that surrounds our Milky Way galaxy could, in fact, be a sprawling metropolis of mirror stars, mirror planets, and perhaps even mirror life, all made of mirror atoms. We are completely blind to their light and their structures because their photons are, in a fundamental sense, not our photons. They belong to the mirror sector. We only feel their collective gravitational presence. It's as if we are living in a world of sound, while an entire civilization of beings made of light exists in the same space, with the only crossover being a faint, universal pressure that we interpret as gravity. This would mean that every galaxy we see is just the visible tip of a much larger, mostly dark iceberg composed of its mirror twin. The concept raises thrilling possibilities for interaction. While the two sectors are mostly separate, there could be very rare and subtle interactions between mirror particles and our particles. Physicists are actively searching for these potential portals between the worlds, looking for instances where a mirror particle might nudge one of our atoms or where a mirror photon might create a faint, unexplained signal. Finding such an interaction would be a monumental discovery, providing a direct window into a parallel reality that has been coexisting with us since the beginning of time. The mirror universe theory transforms the cosmos from a solitary existence into a delicate cosmic dance of twins, a universe and its reflection, forever bound together by gravity yet forever separated by a fundamental difference in handedness, offering a profound and elegant solution to the dark matter enigma. What if the universe is not just governed by physical laws, but is itself a form of computation, a vast and evolving system of information processing? This brings us to a truly 21st century theory, a proposal that reimagines the cosmos through the lens of our most advanced technology. It's the idea that the universe is a neural network, a concept gaining traction among physicists who see striking similarities between the architecture of reality and the structure of artificial intelligence. To understand this, picture a simple artificial neural network, the kind used in machine learning. It consists of layers of nodes or neurons connected in a web. Each connection has a certain strength or weight. The network takes in input data, processes it through these layers by adjusting the weights, and produces an output. Through a process called training, the network constantly tweaks its weights to minimize the difference between its output and a desired result, gradually learning to perform a task with incredible accuracy, like recognizing faces or translating languages. It's a dynamic system that evolves to find optimal patterns. Now, take this concept and scale it up to a cosmic level. What if the fundamental building blocks of the universe, the elementary particles like electrons and quarks, are not just tiny dots, but are themselves the nodes in an immense cosmic-scale neural network? In this view, the entire fabric of space-time and everything in it is this network. The laws of physics, the constants of nature that we work so hard to measure, are not fixed fundamental rules. Instead, they are emergent properties. They are the stable, learned weights of the network after an unimaginably long period of cosmic training. Gravity, electromagnetism, even the passage of time itself, could be behaviors that arise from how these trillions upon trillions of cosmic neurons are connected and how they interact. This leads to a breathtaking question about what lies beyond our universe. If our cosmos is a neural network, what is it processing? What is its input, and what is it trying to achieve? One possibility is that what we perceive as physical reality is the network's ongoing computation. The particles and their interactions are the flow of information through the system. But this raises the need for something outside the system itself, the training data and the objective function. The training data would be the initial conditions or the ongoing input that the universe is learning from. The objective function is the goal, the cosmic purpose that the network is unknowingly optimizing for. Is it maximizing complexity? Is it driving toward the emergence of consciousness? Is it simply striving for stability? The answer is completely unknown, but it implies the existence of a framework or a set of principles that exist on a meta level, beyond the space-time that the network defines. This theory offers a fresh perspective on some of the deepest puzzles in physics. The strange, probabilistic nature of quantum mechanics, for instance, might be a natural feature of a system that is still learning and adjusting its weights. The act of observation, which seems to collapse quantum possibilities into definite outcomes, could be analogous to the network settling on a specific configuration after processing information. Even the arrow of time, the relentless forward march from past to future, might simply be the direction in which this cosmic learning process unfolds. We are not separate observers of a static universe. We are active participants within a dynamic learning system. Our thoughts, our consciousness, might be particularly intricate and self-aware patterns of activity within this universal neural network, localized manifestations of the cosmos becoming aware of its own computational processes. This vision blurs the line between the physical and the informational, suggesting that the ultimate nature of reality might be neither particle nor wave, but a form of cosmic intelligence in the making. But if we are to truly understand what might lie beyond our universe, we must first grapple with what the universe itself is made of. We are accustomed to thinking of space and time as a smooth, continuous fabric, a stage upon which the drama of the cosmos unfolds. But what if this stage is an illusion, a clever approximation of a much stranger and more fundamental reality? This brings us to a profoundly minimalist and elegant approach known as causal set theory, which suggests that the very continuum of space-time is not a primary feature of reality, but a secondary, emergent phenomenon. At the most basic level, the universe may be composed of a vast collection of discrete, indivisible atoms of existence, and what lies beyond our cosmic horizon could be the rest of this immense, abstract network of cause and effect. The central problem that causal set theory aims to solve is the profound conflict between our two most successful theories of physics. Einstein's general relativity describes the universe on the largest scales, portraying gravity as the curvature of a smooth, continuous spacetime. Quantum mechanics, on the other hand, describes the microscopic world of particles, a realm that is inherently granular and probabilistic. The two theories are mathematically and philosophically incompatible, and a major goal of modern physics is to find a theory of quantum gravity that unites them. Causal set theory offers a radical solution by proposing that spacetime itself is not continuous. Just as a digital photograph appears smooth from a distance but is actually composed of individual pixels upon close inspection, the fabric of reality may be fundamentally pixelated. In this framework, the basic building blocks of the universe are not particles or waves, but simple, structureless elements called atoms of spacetime. Think of them as the most basic possible events, the fundamental dots of existence. These atoms have no inherent size or duration. They are purely abstract elements of a set. The only thing that defines them is their relationships to one another. Specifically, the theory is built upon a single, powerful idea, causality. Each atom in the set can either precede another atom in time or be unrelated to it. This creates a vast, cosmic web of before and after relationships, a network of cause and effect that is the true bedrock of reality. The miraculous thing is that from this incredibly sparse starting point, a collection of elements with only a before or after connection, the familiar properties of our four-dimensional world can emerge. The smooth, continuous geometry of spacetime, with its 3 dimensions of space and 1 of time, is not assumed. It is a consequence, a large-scale illusion that arises from the collective structure of the causal set. The theory suggests that the volume of a region of space is proportional to the number of atoms it contains. The passage of time is not a flow, but the unfolding of these cause and effect relationships. Our experience of a smooth, flowing reality is akin to watching a movie. The film is actually a series of still frames, but played quickly enough, our brain perceives seamless motion. In the same way, the universe renders a continuous spacetime from a discrete set of fundamental events. So, what does this imply lies beyond our observable universe? If our cosmos is not a bubble or a membrane, but a particular crystallization of a causal set, then what lies beyond its boundaries is not more space in the traditional sense. It is the rest of the causal set from which our local spacetime has emerged. Our universe, with its specific history from the Big Bang to the present, would be one connected region within a much larger, possibly infinite causal network. Beyond our cosmic horizon, the pattern of cause and effect relationships could be configured in ways that do not give rise to anything resembling the smooth, four-dimensional spacetime we know. There could be regions of the causal set that are so sparse or so tangled that the concepts of space and time become meaningless. It would be a realm of pure potentiality, a landscape of abstract relationships waiting to crystallize into new universes with different dimensional properties. This vision of reality is both austere and beautiful. It reduces the complexity of the cosmos to its most essential ingredient, the relationship between events. There is no pre-existing arena of space and time. The arena is built event by event, relationship by relationship. The theory also provides a natural explanation for several cosmic puzzles. For instance, the arrow of time, the reason why we remember the past but not the future, could be a direct consequence of the fundamental directionality of the causal relationships in the set. While causal set theory is still in development and faces challenges, such as precisely deriving the full richness of Einstein's equations from the causal relations, it represents a powerful shift in perspective. It suggests that the ultimate frontier is not a place but a pattern, and that what lies beyond our universe is an immeasurably vast, abstract tapestry of causality from which all of reality is woven. Continuing this journey into the fundamental architecture of reality, we arrive at a theory that seems to blend the digital and the cosmic in an entirely new way. This idea proposes that the very stability of our universe, its remarkable resistance to falling into chaos, might be due to a form of cosmic cybersecurity. This is the theory that the universe is a quantum error-correcting code, a concept that suggests the space-time we inhabit is not a fundamental substance, but a sophisticated projection emerging from a deeper layer of information processing, designed to protect reality itself from disintegration. To grasp this, we first need to understand the fragility of the quantum world. In quantum computing, scientists work with qubits, the quantum equivalent of bits. But qubits are incredibly delicate. Any interaction with their environment, a stray photon, a vibration, a fluctuation in temperature, can cause them to lose their delicate quantum state in a process called decoherence. This is the primary obstacle to building a functional quantum computer. To fight this, researchers have developed quantum error-correcting codes. These are not simple backup copies. They are clever ways of spreading the information of one logical qubit across many physical qubits. The key insight is that if a few of these physical qubits are disturbed by decoherence, the original, pristine information of the logical qubit is not lost. It can be mathematically recovered from the undisturbed correlations among the remaining qubits. The information is protected because it is not stored in any one place, but is holographically distributed across an entire network. Now apply this principle to the entire cosmos. Our universe is at its heart a quantum system. According to general relativity, space and time form a smooth, continuous fabric. But when physicists try to combine this with quantum mechanics, they run into profound problems, suggesting that space-time should be wildly unstable at the tiniest scales, constantly fluctuating into nonsense. Yet, we observe a remarkably stable, coherent universe. Why? The tantalizing proposal is that our four-dimensional space-time is akin to that protected logical qubit in a quantum computer. It is not the fundamental reality. Instead, it is a stable, error-corrected projection emerging from a vast, underlying network of simpler quantum components. The smooth continuum of space and time is an illusion, a mirage that arises because the underlying code is constantly detecting and correcting for quantum errors, for decoherence before it can disrupt our perceived reality. The universe, in this view, is performing real-time cosmic maintenance to keep itself from falling apart. This idea finds a powerful anchor in the holographic principle we discussed earlier. You'll recall that the holographic principle suggests all the information about a three-dimensional volume can be encoded on a two-dimensional boundary. Quantum error correction provides a stunning mechanism for how this could work. The boundary of a region of space can be thought of as the error-correcting code for the interior volume. The information about every star, planet, and person within that volume is not stored locally inside it, but is scrambled and distributed across the distant boundary surface. Any attempt to disrupt a point inside the volume would require corrupting a vast amount of information on the boundary, which is statistically nearly impossible. The interior spacetime is therefore protected. It is a stable, emergent reality because its underlying information is safely stored and redundantly encoded on a remote, lower-dimensional surface. Our experience of a solid, reliable world is a direct consequence of this cosmic error correction protocol. So, what would lie beyond our observable universe according to this theory? The answer moves beyond physical locations into the realm of abstract logic. Beyond the galaxies and the cosmic microwave background, beyond the limits of our space-time continuum, lies the fundamental logical structure of this code. This would be a deeper, more primitive layer of reality, a domain of pure information and computation where the rules of the code itself are written. Our universe, with its laws of physics, would be one particular stable output of this code, a specific logical state that has been successfully protected from decoherence. Other potential universes with different physical laws might correspond to other codes or other logical states within the same computational framework, most of which might be unstable and quickly succumb to errors. This perspective offers a profound new way to think about the origins of space and time. The Big Bang might not have been a physical explosion, but the moment this cosmic quantum computer booted up and began executing its error-correcting algorithm, generating the stable spacetime we call home. It even provides a fresh angle on the nature of gravity. Some physicists speculate that the force of gravity itself may not be a fundamental force, but an emergent phenomenon, a thermodynamic consequence of this ongoing process of quantum error correction, a side effect of the universe's effort to maintain its coherence. The theory that the universe is a quantum error-correcting code is perhaps one of the most mathematically sophisticated on our list, turning the cosmos into a monumental feat of engineering, where existence itself is a state of delicate balance maintained by an invisible, underlying logic far more fundamental than space or time. And so we arrive at our final destination on this journey, a concept that pushes beyond the very framework of every other idea we have explored. This theory dares to suggest that what lies beyond our universe is not another cosmos, not a higher dimension, and not even a primordial void. Instead, it is a realm of such profound abstraction that our language and logic begin to falter. It is the notion of the great beyond as a meta-law realm, a cosmic foundry where the blueprints for reality itself are forged. In this ultimate vision, our universe, with its elegant laws of physics, is merely one possible outcome, one set of rules generated by a deeper, more fundamental process that operates on a level beyond physics as we comprehend it. Think of it this way: within our universe, we are bound by laws. Gravity dictates how masses attract, electromagnetism governs light and chemistry, and quantum mechanics rules the subatomic world. We are like characters in a video game, operating entirely within the code that defines our environment. We can study the game's rules, we can even exploit them, but we can never step outside the program to question why the code is written the way it is. The meta-law realm is the domain of the programmer. It is the context in which our universe's specific code, its laws of physics, is just one file among countless others. This meta-reality doesn't have stars or particles. It has principles of existence, a logic so fundamental that it defines what a law of nature even means. The constants we find so puzzling, the strength of gravity, the mass of an electron, are not arbitrary numbers. They are the output of a meta-law, a higher-order equation whose variables can be set to different values, producing different universes with different rules. This idea emerges at the farthest edge of theoretical physics, particularly from the quest for a final, unified theory of everything. Scientists hope to find a single, elegant mathematical framework that encapsulates all forces and particles. But this pursuit inevitably leads to a deeper question: why this particular theory? Why does the universe obey these equations and not others? The meta-law realm provides a staggering answer. Our theory of everything is not the final word. It is itself a consequence of a more primitive, more abstract set of meta-laws. These meta-laws wouldn't be about quarks or space-time, but about the consistency and structure of mathematical systems themselves. They would govern the very possibility of having a coherent, stable universe. Some configurations of these meta-laws might allow for universes with 3 dimensions of space, while others might permit 7. Some might generate laws that lead to complex structures like stars and life, while others might produce barren, fleeting realities that collapse instantly. The implications are perhaps the most humbling of all. It suggests that our entire scientific endeavor, the magnificent human project of uncovering the laws of nature, is ultimately the study of local bylaws. We are deciphering the regulations of our particular cosmic township, completely unaware of the constitutional principles that establish the entire system of governance. This meta-realm is the ultimate answer to the question of fine-tuning. Our universe isn't fine-tuned by chance or design. It is simply one valid solution generated by the immutable meta-laws. In an infinite landscape of meta-possibilities, a universe capable of asking about its own origin was an inevitable outcome. Ultimately, this theory leaves us at the precipice of understanding. To ask what lies beyond the meta-law realm is likely a meaningless question, as the concepts of beyond and before may themselves be products of the very rules generated within it. We are left with a universe that is rational and ordered, not because of a divine plan, but because it is a logical consequence of a deeper, perhaps even more beautiful, abstract truth. Our reality, in all its splendor and complexity, is a shadow cast by a light shining from a realm where mathematics, existence, and possibility are one and the same. So, from an infinite multiverse to a cosmic simulation, we have ventured across the landscape of 25 of the most incredible ideas about the ultimate frontier. We have stood at the edge of our observable universe and peered into the abyss of possibility, contemplating bubbles of reality, cosmic holograms, and even the chance that we are minds in a grand computation. Each theory, from the quantum flutter of a Boltzmann brain to the majestic cycles of an ekpyrotic universe, represents a profound attempt to answer humanity's oldest and most haunting question. These are not just flights of fancy, they are logical extensions of our deepest scientific principles, pushed to their absolute limits. They show us that the cosmos is far stranger, more vast, and more mysterious than we could have ever dreamed just a century ago. The truth, as it stands today, is that we may never know for sure what lies beyond our cosmic horizon. The very nature of these theories often places them, for now, beyond the reach of direct observation and definitive proof. We are like ancient mapmakers sketching dragons and legends at the edge of the known world, guided by logic and imagination where our instruments cannot yet reach. Yet, this uncertainty is not a failure of science, it is its very engine. The pursuit of these answers, the relentless questioning and the bold hypothesizing is what drives our understanding forward. It forces us to build more powerful telescopes, to devise more elegant equations, and to challenge our most basic assumptions about existence itself. This quest expands not only our knowledge but the very boundaries of our imagination. Ultimately, the journey through these theories reveals something fundamental about us. Our longing to know what lies beyond is a testament to an unquenchable curiosity, a defining trait of our species. It is the same spark that compelled our ancestors to wonder what lay beyond the next mountain or across the uncharted sea. Now we gaze into the cosmic ocean, daring to map the impossible. Whether our universe is one of many, a complex simulation, or a mathematical structure, the act of seeking connects us to every explorer who has ever lived. The greatest discovery may not be the final answer, but the ever-deepening appreciation for the magnificent puzzle we are a part of. What theory resonates most with you? Does the elegant dance of brains capture your imagination, or does the profound simplicity of the null universe strike a chord? Let us know in the comments below, and don't forget to subscribe for more journeys to the